Definition 18.4 is going to show us a growth function, exponential growth function that would be analogous to going straight from the beginning balance to the ending balance for an investment. In example 18.10, we had talked about Rob's 4-year investment. He started with $400, ended with $473.35. And we had to go through that process 1 year at a time. But this formula is going to allow us to be able to go straight from the beginning all the way to that final step in just one calculation if we know enough information about the investment. So the kind of things that we need to know about the investment are the starting amount. The principal is the starting amount for your investment. Now this is a special type of circumstance where you're not going to be adding money in to your investment as the years go on. This is just a single one-time start with this amount and leave it in the bank for a certain amount of time. And you will have a fixed interest rate. Your interest rate would not be variable, and that's represented here by little r. And the number of times the interest is compounded per year can also be taken into account, because banks don't always just do that one time a year. Sometimes they do it 12 times a year. They do it every month. That's the kind of calculation that's done in a savings account. If you have a savings account or checking account with a bank, you get statements every month. That's because they give you the interest, if you earn any, every single month. So there are a variety of ways that you can get compound interest into your account. So that's accounted for here with the letter N. And then T represents the number of years for your investment. And then capital A is oftentimes what we're after. It's the amount that you have in your account after the T number of years. So example 18.11 is going to give us a chance to see how this calculation works under different compounding schedules. So it starts with saying a sum of $1,000 is invested. That represents your principal amount. That's your initial amount that you're going to be investing at an interest rate of 12% per year. And we would want to make sure that we represent that as being r equals 0.12. We have to represent that in decimal form. And then find the amounts in the account after 3 years. That's going to be T. If the interest is compounded annually, semi-annually, quarterly, monthly, and daily. So when we have a annual compounding schedule, that means we only compound once a year. That would be n equals 1. Semi-annual compounding schedule means that we're going to do it twice a year, n equals 2. Quarterly, 4 times a year, n equals 4. Monthly, n equals 12. And then daily would be n equals 365. You can even have things like weekly, bi-weekly, lots of things that we can do here. But this will give us plenty of opportunity to see how this calculation works. Now, every single one of these calculations has the same starting amount, has the same interest rate, and has the same number of years. All we're doing is comparing how the different compounding schedules will give us different values for the amount at the end of the investment. So I'm going to come up with a general formula for this. So we have A equals capital P, and I'm not going to write capital P, I'm going to take that away. I'm going to put 1,000, where that goes, times 1 plus R, which is 0.12, and then I'm just going to leave N as a variable for right now, because that's what's going to change as we end up doing the different calculations. And then for the exponent, we're supposed to have n times t, so I can represent that as 3n. So it has a similar structure to what we saw with that Euler's number calculation, where that was the 1 plus 1 over n raised to the n. Not exactly the same, but very similar. And now we would be interested in plugging in the different values. So, for example, if we do part A, where we let n be equal to 1, then we're going to end up with A equals 1,000 times 1 plus 0.12 over 1, and then raised to the 3 times 1, which is going to end up being 1,000 times 1.12, all raised to the 3. And I will typically do this same calculation with simplifying the exponent first, and then simplifying everything that's going to be a part of the base, and then just leaving the multiplier of 1,000 out there in front. And then this I can actually type in the calculator all at one time. And this is going to end up giving me, let's see, $1,404.92. So this is the calculation that goes directly from the beginning amount of 1,000 all the way to the final amount at the end of the 3 years. You can do that same calculation for part B by letting n be equal to 2, which is going to give you A equals 1,000 times 1 plus 0.12 divided by 2 raised to the 3 times 2. So this will be 1,000 times 1.06 raised to the 6. And then that is going to give us an amount of $1,418.51. And that was the situation where we compounded twice a year and not just once a year. So it would appear that the more we compound in a year, the better the final result is going to be for the investment. So let's see if that trend continues. For part C, we have n is equal to 4. And I'm just going to go ahead and tell you what the answers are for this so we can see the pattern. If you need to practice the calculation, I would suggest pausing the video and practice the calculations so I don't spoil the results for you. For n equals 4, you're going to get an amount of $1,425.76. So we see a better result here as expected. For part D, if we let n be equal to 12, we will get a ending amount of $1,430.76. And then finally for part E, where we are compounding every single day, we are going to end up with $1,433.24. So even though we made a really drastic jump from part D to part E, going from 12 times a year to 365 times a year, notice that we don't see a really dramatic jump in the end result. It's only less than $3 over the entire course of the 3 years. So the amount of increase that we see does start to slow down, just like we saw the increase slow down in the calculation for Euler's number. So there is a great deal of similarity in the calculations because of the way that the base and the exponent are formulated here.